We're going to work on electromagnetic energy practice problems. This chapter usually has many formulas, but we're going to focus on three main ones. This first formula is C equals lambda times nu. Lambda and nu are Greek letters, and nu is more like a rounded V. C stands for the speed of light, 2.998 times 10 to the 8th meters per second. Wavelength should be in meters, and frequency is going to be 1/seconds or hertz. The second formula is energy equals H times C over lambda. H is Planck's constant, 6.626 times 10 to the negative 34 joules times second. C is the speed of light, and lambda should be in meters. So when the units cancel out, energy should be in joules. This third formula is lambda equals H over m times V, and V here is the English letter V. M is mass, and up to this point we're usually dealing with mass in grams, but to use this formula, mass has to be in kilograms. V is velocity, meters per second, and H is Planck's constant. But we need the units to cancel out, so we need to convert Planck's constant to different units. Luckily for us, Planck's constant has already been converted for us. So when we're using this formula, we're using this Planck's constant. 6.626 times 10 to the negative 34 kilograms times meters squared over second. This will give us lambda in meters. Let's try an example. Calculate the wavelength of light that has a frequency of 5.2 times 10 to the 12th per seconds. Let's start off with our given. It's asking us to calculate the wavelength, so that's my question. And it has a frequency of 5.2 times 10 to the 12th per seconds. And I do know that we're going to be using C, the speed of light. So I have many formulas. I have lambda and I have frequency. So I'm going to use C equals lambda times frequency. So C is a given. My lambda is my unknown, and my frequency. So I'm going to go ahead and solve for lambda. Lambda equals 5.8 times 10 to the negative 5th meters. Remember when we're trying to use our calculators that you do want to use parentheses around your scientific notation. Let's take a look at another example. What is the energy of red light with a wavelength of 632 nanometers? I'm going to start off with my given. What is the energy? That's my question. Wavelength is lambda, so that's 632 nanometers. I'm going to go ahead and list Planck's constant. And I'm going to go ahead and list my speed of light. I have a formula that relates energy to lambda. That's that second formula. However, my units are not correct. Lambda should be in meters for units to cancel out. So I'm going to have to convert nanometers to meters before I can actually use the formula. If nanometers is in my numerator, then nanometers has to go in my denominator. 1 nanometer is 10 to the negative 9 meters. So I can go ahead and multiply, and I will get 6.32 times 10 to the negative 7 meters. Now that all my units are correct, I can go ahead and plug into a formula. Energy is my unknown. I'm going to remind myself to use parentheses. And energy equals final units have to be in joules. Let's take a look at another example. What is the wavelength of a particle that emits 5.25 times 10 to the negative 19 joules? Let's start with our given. What is the wavelength? That's my question. And 5.25 times 10 to the negative 19 joules. Joules is the unit for energy, so that's information of energy. I'm going to go ahead and list my Planck's constant. I'm going to list speed of light. And I do have a formula that relates energy to wavelength. All of my units are correct. So the formula is energy equals hc over lambda. I'm going to plug in what I do know. I'm going to solve for lambda, and my final units for lambda should be in meters. Let's take a look at another example. Calculate the wavelength of a softball with a mass of 100 grams traveling at a velocity of 35 meters per second, assuming that it can be modeled as a single particle. We need to start off with our given. Calculate the wavelength, that's the question. Mass of 100 grams. Mass equals 100 grams. And it's giving me velocity. And I'm going to go ahead and list Planck's constant. All right, before I move on, I have to take a look at my units. Because Planck's constant is in kilograms, that reminds me to convert my mass to kilograms. So I'm going to go ahead and convert my mass to kilograms. Grams in the numerator. 1 kilogram is 10 to the third grams. So this will give me 0.1 kilograms. Now that all of my units are correct, I can go ahead and plug this into a formula. And my final units is in meters. Good luck and keep practicing.